Today we want to talk about descriptive statistics. You know, the last time on Tuesday, we talked about the basic concept of statistics. And here we talk about statistics being divided into descriptives and inferential statistics. We also talk about relationship between statistics and probability. So when we talk about descriptive statistics today, well, it's a little bit lengthy. You may not be able to finish it. Continue and finish on Tuesday. While after that we now start talking about probability before we move to inferential statistics. This is one of my maxims. Statistics and management are two faces of the same coin, which is evidence-based decision. Statistics provide the evidence while management makes the decision. Now, the first thing we want to talk about descriptive statistics is the concept of distribution. And it's so fundamental to descriptive statistics. We already said that it's the aspect that deal with summarization of the data. Now, the first thing you do with data after you have collated, and even clean the data, the first thing is to understand the distribution of each variable. So distribution, it applies, as you see, it applies to each of the variable or each of the phenomena you study. For example, age, you have to talk about distribution of age or age distribution, sex distribution, marital status distribution, distribution of religion, ethnicity, education, the knowledge of anything we are doing, adherent to antiretroviral, whatever, any variable you are studying, any variable that is part of your study, each of them has distribution among the sample size, the total subject or participant. So the meaning of distribution is the pattern observed in a collection of values for a variable. Pattern observed. So for each of the variable, see, that's why it is variable. Say that you can assume any value. All the elements, all the participants, all the people, subjects cannot have the same value of a particular variable. That's why it's variable. If all of them have the same value, it's not a variable, it's become constant. For example, if you are studying women that go to antenatal, they are all women. So sex is not a variable because sex is constant. You cannot say, oh, if you ask all of them are female. There's no way any of them will be male. So in that situation, sex is a constant. So a variable, all the participants cannot have the same value. That's why it's very. Now, the pattern observed in the collection of the value, those values, different values, each of them, but of course, if there are plenty, many enough, some will have the same. For example, one person, if you are dealing with 400 people, what is the sex? Some will be male, some will be female. So that's the only two possible values. So you have some people that will be male, some will be female. So what is the pattern? How many are male? How many are female? If it's the skin color, well, some will be light, chocolate, dark. Some will be, how many of them have that? Each of the value. If you talk about weight, that one is even very more because you can have many weight, but you can still see some that have the same weight. So some will be 70, 71, 72. You may have more than one that is 70, have more than up to 10 that's 72 or whatever. The pattern of the value is the distribution. So often we see the various value in a data set. Now, this distribution there are 4 types. Even the pattern, there's 4 ways of describing it, or 4 types. The first one is frequency distribution. The second is relative frequency distribution. The third is cumulative frequency distribution. The fourth is cumulative relative distribution. Now, this example I give here will illustrate and make you understand distribution itself and the different four types of the distribution. Here we have 50, the sample size says 50 women, and what we are showcasing here is the parity of the women. Parity for some of us that are non-medical people, parity is the number of times a woman carry pregnancy to term. When I say to term, to maturity, forget about how the child was delivered, that CS or vaginal delivery, it doesn't really matter, or whether the child is alive or not, it doesn't really matter. Number of times a woman has carried pregnancy to term, that is meaning of parity for that woman. So if a woman has not carried pregnancy to term, the parity is 0. If it is once, it's 1. If it is 2, it's 2, and so on. Now, it's different from number of pregnancy. Somebody can have, maybe I might have been pregnant many times. If the pregnancy does not lead to, does not come to term, maybe there's abortion, miscarriage, or whatever happened, that one is not part of the parity. It's the one, the number. If you have been pregnant 8 times, if it's 2 times that you carry to term, that's the parity. Now, I think you understand the meaning of parity now. So we want to look at distribution of parity among 50 women. You can see the first column is the parity itself. The value is what's your parity. Some will say it's only once, that will be 1. Some none, will be 0, 2. We have up to 5. It can be more than 5, but here we stop at 5. The people out of the 50, we just have possible value from 0 to 5. So the 6 possible value for this data set are 0, 1, 2, 3, 4, 5. Now, the frequency distribution here now. You see, after that first column, the blue column, the red or brown, the brown, they call it, whatever, all these different colors are, each of them denote frequency, relative frequency, cumulative frequency, cumulative relative frequency. So the frequency distribution for this parity, you can see for para 0, those ones that have not carried pregnancy to term at all, they are 15 out of the 50. For 1, they are 11 out of the 50. For para 2, they are 8 out of the 50. For para 3, they are 6 out of the 50. For para 4, they are 5 out of the 50. For para 5, they are 5 out of the 50. Now, you will see that the number out of the total sample set that fall in each, that has each value, is the frequency. So the frequency of 0, that is those who have not carried pregnancy to term, is 15. The frequency for this one, for para 1 is 11. The frequency for para 2 is 8. For para 3 is 6. For para 4 is 5. For para 5 is 5. If you had all the frequencies that I give you the total sample size, they are 50. Now, the major problem with this frequency is that, assuming another person did this work now, and there are 150 people instead of 50, how do you compare? If here now we say para 0 is 15 people, and out of the 150, para 0 is 25. How do you compare? You cannot just say 25 is more than 15. But you have to say 25 out of 150 is smaller than 15 out of 50. Are you see now? So because different study, if any of you do the same study now at different time, you are going to have, you may probably, yes, most likely have different sample sizes. So there's no way you can compare para 0 between the study or para 1 between the study, unless you bring an intelligence into it. And the intelligence, intelligent people now brought into it was that, okay, instead of talking about the absolute number, the frequency, let's talk about put the frequency over total to know what percentage of total is that frequency. Like for example now, 15 that has para 0 here, you say 15 over 50 plus 100% to give you percentage. The same thing, if you were maybe another person that did the work, maybe it's Oluremi Tosin that did the work in Lagos, and Yeah, 150 is dealing with 150, not 50. In that situation, you say para 0, 25 of them have para 0 in our own study, you will not say 25 over 150 times 100%. Can you see? So by the time you express each of the frequency in percentage, it will be easy to compare across study. So after all, in history, when you are quoting the study, you are not going to be asking for the sample size. It's the percentage. You will compare. If the percentage is the same, of course, we know that they will not have the same sample size, but it's the percentage of each frequency you are looking at. That frequency divided by the total, the sample size times 100, which is expressed by saying is called relative frequency. Can you see now? So that is the second type, the relative frequency. So relative frequency will enable you to compare results across different studies. That is why when you are quoting, oh, you say Ngozi Emeka et al., the work done in Owerri, this is so and so. Now, you quote in percentage. You quote another person that did something in Lokoja, you use percentage. You quote another person in Maiduguri, you use percentage. Another person in Ibadan, you use percentage. So you'll be able to compare. You forget about their sample size. Then you have used it because you have expressed your frequency in percentage. And that's the commonest one that makes sense. That is relative frequency. But there are still, that's the common one. If you, most of the time when you calculate your result, you see the frequency, you see the value of the outcome, the possible outcome for the variable, like for this one, 0, 1, 2, 3, 4, 5. Then you see the frequency in another color, you see the percentage, which is the relative frequency in another color, which is the one you use to compare. Now, most of the time, you don't see beyond this story. But there are still other two that I will tell you by the time we finish explaining the reason for them. The reason for them. So now, in cumulative frequency now, instead of you look at it, instead of you look at number one, this frequency here is 15. The relative frequency of that number one is 30%. Then cumulative frequency is 15 because that's 15 that is there. But if you go to number two, please Gani Oseni, please mute. So if you go to the second one, which is 1, para 1, the frequency is 11, the relative frequency is 22. But you will see that when you come to cumulative frequency, that is like accumulative. So you had the 15 with 11, it gives you 22. It gives you 26 rather. You had the 15 to 11, it gives you 26. Can you see? So now, when you now come to the third one, which is para 2, there are 8 of them. The frequency is 8. The relative frequency is 60. But the cumulative frequency, you now have that 8 to the 26, the last one, make it 34. When you come to para 3, you have that 6 to the last one, which is 34, to give you 40. When you come to para 4, you had the 5 to the last one, which is 40, to give you 45. Why, when you now look at the last value, which is 5 para 5, and it's 5, the frequency is 5, you had to the 45 to give you 50. And you see, at that last, that is the total sample size. So you are going up, you are adding the total, the initial total with the current one. That's what we call cumulative frequency. But the cumulative frequency is as useless as the frequency if you do not express it as percentage, the way you express frequency in percentage and become relative frequency. So it's the same thing, you express cumulative frequency as percentage to give you cumulative relative frequency. So the way you are actually using there is the cumulative relative frequency. And what is the rationale? Why you have to be adding? Why not just use the relative frequency or frequency relative with this relative frequency? Why do you want to be adding this cumulative? Why do you want to be adding? The reason is very simple. You want to be able to say at least, at most. You know that most of the time, the people that take decisions, somebody shouting, maybe you don't understand or whatever. Okay. Now, for example, most of the people that take decision are in a decision-taking position. They may not be as, when it comes to, they are smart. Not that they are not smart in their way. Politicians, If they are not smart, they will not continue dominating the way they do. But they may not have time, or they may not be technocrat like you. They may not have time for some of these scientific terms. Imagine now, you are commissioner for women affairs or health in your, or whatever in your state, and you are having some program for women, and it has to do with their parity, maybe number of times they carry pregnancy to term, and you now decide and now say, okay, I want to. By the time you give the budget, you give the plan, they say the governor now say no, 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 it's too much. We don't have that type of money. Why can't we do it for some of them? Maybe people that have given, maybe maybe para 2 and 3 and above. Can you see now? He doesn't want everything because the number is too much. Maybe we are talking of thousands of people now, and the sample size, the people you want to do this thing for. And I say, why are we not looking at people that are maybe para 3 and above? You know, imagine, or maybe people from 0 to 3. I can just leave the others. So will you be in the need to say, oh, okay, for para 0, they are 30% of them are para 0, while one is para 1 is 22%. Para, you tell it, it doesn't have time, for you to even see that type of person. They may give you 2 minutes to see. So it's not, you begin to ask him to be cracking brain. So you want to be able to say, oh, if that is the case, anything that at least para 3, you now see 80% of them is at least para 3. Can you see now? At least mean that 3 and below. So that's what is done from 0 to 1 to 2. Is at each level you keep on adding. If you look at it now, para 0 is 30%. At least para 1, that is mean 1 and 0, making 52%. At least para 2, making 0, 1, 2, it makes 68%. At least para 3 is 80%. At least para 4 is 90%. But the same way you can do in the other opposite way. At most, oh, sorry, it's not at least. All these things I'm describing is at most. At most, para 1 is 52%. At most, para 2 is 68%. At most, para 3 is 80%. But if you want to solve at least para 2, what will you do? You will now know what at least para 2, you have to do at most para 1. At most, around 52%. Remove 52 from 100% is from 48. You know, oh, at least para 2 is 48%. Because you already know up to 1, which is 52%. The way remove 52 from 100, it gives you 48%. If you want to say at least para 3, you have to know at most para 2, which is 68%. You remove it from 100, it gives you 32%. You now know that at least para 3 is 32%. If it is at least para 4, you want to look at. If you know at least at most para 3, which is 80%, remove 80% from 100, it gives you 20%. Does it make sense? That is it. So the cumulative frequency issue or cumulative relative frequency just allow you to be able to say at most what proportion are these particles. That's all. That's the reason for it. And we proceed. If there's any question, let me know. Now we have talked about distribution. So that is what you do for each. When you are saying distribution table, that's what you do for each. The first thing you do for all your variable is to know the distribution of each variable, each phenomenon you study in your research. Now, how do we present this distribution? So, just a minute. My light is affecting my vision. Let me just switch over. Hello, can you hear me? Can you hear me? If you can hear me, let me know.